Hello everyone, and welcome to part 4 of the Atari project. In this video I'm going to focus more on the 3D printing and 3D modeling design aspect. So I've got my computer desktop here. At work I use a program called Pro Engineer Creo. It's made by a company called PTC. But here at home I just use a free program called Autodesk Fusion 360. And if you are a maker like myself and your business, which I don't really have a business, makes less than $100,000 in a year, which I absolutely qualify for, you can use this fully featured software for free. So I am by no means an expert in this. The workflow is a little bit different and not quite to my taste. But it was a free program and it is pretty powerful. It's very popular in the maker community. So I will just walk through quickly how I made the backplate of the Atari with this program. One nice thing down here at the bottom, you can see a timeline. So this will go step by step through each feature creation as I make the part. This is really useful for stepping back in time if you need to make adjustments later. And it also gives me a chance of having everything done ahead of time, and then I can walk through each step that I did. So first thing is a sketch. So almost every 3D modeling program that I have used, especially any ones that are actually used in industry, start with a sketch. And this is literally just a 2D drawing. You could think of it like something drawn in paint. And then things don't become 3D until later on. You don't start with a 3D object. You start with something in 2D and you draw it on a plane, and then we work with it from there. So starting with this, I started with the easiest part of the back plate, which is the cutout where the I/O panel needs to go for the computer. So I took the measurements of the I/O panel, and that's in this smaller rectangle here. And then I took the outer dimensions of the Atari itself and the height of it, where I wanted this panel to extend to, and put that on the outside. And then I took some measurements between here and here to make sure that I had the plate located exactly where I wanted to in reference to the Atari as a whole. So this is kind of the easiest place to start from. So whenever I'm creating a 3D model, I always start with the easy stuff first and then build from that. So this is a large flat piece. This will end up just being a hole, which you'll see in a second. And it's a good place to start from because everything kind of builds from where this plate is located. So once you have a sketch, we create an extrusion. So you go up here and you go to extrude, and then you select the body that you've just sketched out. Now note, I could have selected in here, so if I go and I create an extrusion and I say I want to select this inner box, here you can see I can make a panel out in that, out into space. However, if I pick the area here, which is really where I want my panel to be, the software will automatically assume that this rectangle is just empty space. So we'll cancel out of that. So I'm left with a panel that's perfectly sized for the I/O panel. So from here, I need to fill in the sides. So I went and I just made a really simple, let's try to spin this around. That's the other thing I'm getting used to in Fusion 360. The way their orbiting tool works is a little weird. So the Atari itself comes down and roughly features in like this. Maybe I'll show a quick side shot. You can see what that looks like. So I start with very simple shapes here. Now the actual Atari itself has curved features in here and some nice radiused edges. We're not going to worry about that right now. We're just going to start with the basic raw shapes. So taking measurements for here, 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 and here, Note that this is not actually a vertical line. It is slightly convex out to this point. So this point is farther from here than this point is. Starting from just using my calipers, I made the basic measurements in here so you can check the dimensions of that. If I open up this sketch, you can see the dimensions that I took from my measurements here. So the calipers, I measured 0.56, 1.41, 1.62, and 0.72. The other thing that you need to look out for when you're making these sketches is that everything turns black in here. And that means that the sketch is fully defined. Now what I mean by that is this, if I wanted to move this wall out, you see I'm clicking on it right now and I can't move it anywhere because it is fully defined where it needs to be 0.56 inches away from this line here, and the end of it here is 0.72 inches from this line, and the end here is perpendicular to this edge here. That fully defines this line and it can't move anywhere. Now if I said I delete this, you see that this turns blue. Now I can drag this around because the software doesn't have any limits on where it can be. So you can kind of think of this in terms of like stop blocks on a car. If you want to keep the car from rolling away, you jam blocks in the wheels, and that fully defines it and fixes it in place. The dimensions are doing the same thing in here. So I will just undo that. You see it is black once more, and now this sketch can't move anywhere, and it won't have any unintended movements later on, which will be important. So now we'll jump out of that sketch, and we need to extrude this. This is done the same way as before. The next thing I did was create the mirror edge of that. So I just created another sketch, but this sketch is driven by the view of the sketch behind it. So if I jump into this, you can see here that I just grabbed the points of the other geometry behind it and said be the same. So whatever changes I make to the first sketch, this sketch will follow. And then I extruded that to give it a thickness. As far as how thick to extrude stuff, obviously that'll depend on what you're creating, but for this panel I chose 100 thousandths thick. That's 0.1 inches. That's a thickness that my 3D printer can do really well. It makes a nice strong part that doesn't flex or dimple in during printing. So I usually use about 0.1. You can go as small as say 0.06, but you're getting into really thin prints at that thickness, and it's possible that you'll see some warpage in the part or breaking later on. Okay, now that we've had the wall thickness defined and we have our two side walls here, we need to make a top and a bottom. So I made a sketch, again grabbing the sketches of the sides that I already have here, since I know that just this big rectangle will be the floor. And I extruded that, as you can see there. And the next part was making the top. You can see here I just grabbed the sides and the back wall, extruded that, and you can kind of see this start to take shape. Now let's get back to the complicated features on the back of the Atari, like the curves that come around here that we didn't address earlier. We're going to use the fillet tool. Now I know it seems like it would be fillet. In engineering terms, this is actually pronounced fillet. It's weird. If it's a fish fillet, it's a radius fillet. I don't know why it's that way, but that's the correct pronunciation of it. So I like to add fillets on the insides of boxes like this, especially with 3D printing, because it's adding some strength in here for free. So as the 3D printer moves up around here, it's going to make this nice little curve. It adds some stiffening to the corners here, so you don't have quite as much of the stress right in the corner, and you can add some extra thickness into the part that's not noticeable at all, but it will really help make this a nice stiff part in the back here. So I just simply selected all of these edges, and then the tool created the radius in here. Now the actual dimension of the radius doesn't matter a whole lot. I kind of just picked nice round numbers that look tidy and don't mess with anything else. Like I didn't want it to extend over into here and get in the way of something. In this case, you can just sort of pick whatever number suits the part and you like. And I made some curves on the outside here. This just makes the surface nice and smooth to the touch, so it doesn't have sharp edges around here. It also matches the aesthetic of the Atari that doesn't have too many sharp edges. If you look at the plastic, everything is nicely radiused out. Then I guesstimated what the radius of the sides was. And this is where and you can see this in the video number 3 of the Atari, I printed off a lot of test pieces to try and get these edges in here exactly right. And you'll see what I did that and how I did that later on here. So from here, we're done. This is ready to be 3D printed. And if I was all excited, ready to go, I could have gone off and printed this whole thing and probably spent 12 hours or so, and maybe it would fit, but maybe it wouldn't. And like I said, I didn't know these exact radii perfectly to mate to the part. So in this type of situation, I like to do some small test prints of just the features that I'm trying to test fit before I do the full thing. So the rest of these features down here show how I did that. So in this case, I just made a small box that encompassed the edge. And this sketch is a large plane that goes around the entire outside. Now the actual size of this doesn't matter. I just wanted it to be bigger than the entire part. And lastly, I have an extrude. So what I could do with this extrude, if I edit it here, now that I have this nice big plane that I can drag, I can say to create a cut, and I am going to slice down my part to just the little piece that I care about. So say I need a test piece to measure the edges and make sure that I get this side profile correct. I am going to take just enough of a slice. That should be fine. Hit OK. And now all of this, you see the sketches are still out here. The data is there, but what's actually seen by the 3D printer is just this little part that will print off in a few minutes, and then I can test fit this up to the up to the Atari. And I did that for a few different pieces. So I did that for the sides to make sure that those fit snugly up against the back, and it's a good thing I did, because I did actually need to adjust these dimensions a few times. And I also did it for this back plate here, since I wanted to make sure that the computer I/O panel snapped in nicely. The other more practical thing I ran into is this is actually a larger part overall than my 3D printer can print in one go. So let's look at what that process is. So I have my whole bracket here. All right, we are ready to print. So in Fusion 360, simply go to Make 3D Print. This creates what's called an STL, or stereolithography file. In many other softwares, you would just go to File, Save As. In this case, because of the way Fusion 360 in particular works, that's not what I need to do to export an STL file. But 3D printers in general, the slicing software will only read STLs. Sometimes there's some software that will read other file types, but STL is the file type of choice for 3D printing. It's sort of like the raw file is to photography. So we'll go to Make 3D Print, and we need to select the part, and it will think. Now you can see all of these lines going everywhere. And if you zoom in really closely, you can see that it's actually a lot of triangles. So that's what this number of triangles is. And what an STL file is a number of data points in space that create triangles. So the software has converted the solid geometry into the surfaces that is just lots and lots of triangles, makes a nice lightweight file, and this is what our slicing software will read. So I am going to not send it to a 3D printing utility. Actually, I will. This is a nice benefit of using Fusion 360 if you can have it directly send and open up your slicing software. Note that this file alone is not enough to work with the 3D printer unless you're using some of the built-in functions that are directly compatible with Autodesk, but my printer is not. So I'm going to have it open Simplify 3D. So, as I said, cannot auto range. Largest part exceeds build dimensions. Yes, this is too big to fit my printer, but I don't care. And you can see what I did in there before. So this is where I use that plane to create two different pieces. Let me move these around a little bit. Here and here, you can see if I spin this, I made a seam. And then after the fact, I can glue these together, sand, finish, and make this a nice single piece. So we'll just get rid of those for now. Now, Simplify 3D is 3D printing software. It's a slicing software. It is not free. I think it is about $150. I consider myself somewhat of a 3D printing power user, so I benefit from a lot of the features that are in Simplify 3D. However, most 3D printers come with their own software, or you can use free software like Cura or Slicer. There's few different options out there, and if you search around on YouTube, there are lots and lots of tutorials on how to use different slicers, what different slicers are best for what things. Personally, I'm a huge fan of Simplify 3D, and I like the way that their workflow is, and I also find that the way it creates the 3D printing commands, you end up with some very, very nice parts. So now that we have the model dropped into Simplify 3D and we've got it oriented how we want it, excluding the part that it runs off the edge here, let me quickly go over some of the common 3D printing settings if you're just getting familiar with 3D printing. Now this is going to look like a lot of information, and again the software that you use might be different from that. I'm just going to go over some generic numbers, so don't read too much into the exact settings that I have here. There's still somewhat of an art form to 3D printing, so your mileage may vary a little bit, but I can go over some basics as far as layer heights go and infill and support structures. So I printed this part in PET, so I have some preset profiles here that just set up a lot of different parameters depending on different materials I have. So I have this already defined for PET. And here's what I do for sort of a typical kind of print. I'm not looking for extreme high resolution here. There's not a lot of complicated details, so I don't need to go down to the super low layer heights. So if I go to a layer here, I am printing this at 0.2 millimeters or 200 microns. And that's pretty standard for FDM printers. I always like to have 3 shells. You can go as low as 2. I really recommend against doing 1 shell. Shells are the number of layers around the outside. So the most of the time you're not going to be 3D printing a fully solid part, and that gets into the infill, which I'll cover in a second. Shells are how much skin is on the outside before you get into the relatively hollow inner core. However, in a part like this, you could think of this like a sheet metal part. It's so thin already that 3 shells basically just makes this a solid part. And I use 3 shells for just about everything unless I need to make something really super strong, and then I might do 5 shells. So what that means is this will have 3 solid layers on the bottom, and then it will make 3 passes around the sides, and it will make 3 solid layers on the top. Now there is a difference between the two because the top and the bottom, so the bottom here and the top, which is just this line here, those are going to be 3 level heights thick, whereas the sides here will be 3 nozzle diameters thick. And maybe that will be the exact same overall thickness, or maybe not. My nozzle is 0.4 millimeters wide, so that means that 3 shells I'm going to have 0.12 millimeter wide walls. But then with layer heights of 0.2, that means I'm going to have 0.6 millimeters thick top and bottom. So you could end up with some differences there. In reality, you're not going to notice a difference. But if you're really digging into the strength of a part, it might matter. The next thing is infill. So I typically use about a 25% infill, which some people might find a little bit aggressive or not enough. But it's a good average. I use it for just about everything. It's a good balance between strength and speed. Supports, this part right here I purposely oriented in this way so it will not need any support structure. We don't have any overhanging features. And the temperature that I like to run PET at is 240 Celsius, and I run a pretty hot print bed at 70 C. Actually, even hotter would be better, but I tend to run into thermal overloads on my print bed if I go up beyond like 80 degrees Celsius or so. So I stick with that. So let's take a look at what this looks like in the end. So here is the calculated path and sort of a sneak peek of what this will look like after being printed. Let me cut down through the bottom here. So this is what I mean by infill, and this just saves on filament and speed. I'm not really losing that much strength in the part by having this honeycomb infill in here, and it really speeds up the printing process. But as far as the shells go, as what I said earlier, if I scan down here, you can see how it prints 1 solid layer and then comes back and does 2 solid layers, and then 3 solid layers, and then it starts doing the honeycomb. And then the top part will come up, so 1 layer, and then 2 layers, and then 3 layers. And then for the sides, you can see 1, 2, 3 shells along the sides there. So that's what I meant by the shells features. And you can see this just represents the printer head moving back and forth. And it estimates this will take about 6.5 hours and use a bunch of filament. So now that we have our printer file ready to go, we simply save toolpaths to disks, and I can save this to a SD card and plop it in my printer. I use a printer server that I'm not going to cover over here because it's beyond sort of the beginning 3D printing, but the majority of home 3D printers have an SD card port, so this just lets you save it to an SD card, and then you can plop it in your printer and you're ready to go. And that is the basics of how to 3D print. Start from an idea and how to 3D print things.